Welcome. In this short video, let us look at a simulation of the coin toss experiment. Specifically, what we will do is we basically generate a random variable that follows a Bernoulli distribution and try to identify or estimate the value of the probability parameter P. That is the probability value P from these n trials. That is, we are looking at a random variable X that follows a Bernoulli distribution with a parameter P. So our goal is to find the value of P from, that is, we want to find P from n trials, that is outcomes from n trials. So if the outcomes from n trials are denoted by xi, that is xi are the outcomes from n trials, the I is equal to 1, 2, then the probability estimate, that is probability estimate after n trials, is given by the average of the values, that is the average of the outcomes. I is equal summation I equal to 1 to n, I is equal to 1 to n xi, and then divided by n. So this is like the arithmetic average of the outcomes. It gives us the estimate of the probability. We learned this from maximum likelihood estimation, that is MLE, estimation of P. You can look at this derivation in a previous video. Now let us look at writing a MATLAB code for finding this value. So the key step is first, the key for finding this Pn using MATLAB is we have to generate this xi sequentially, that is we generate these random variables using a Bernoulli distribution, and then we try to find the value of P hat sequentially. So for that we need a sequential formula which can be easily written as Pn hat is equal to n minus 1 by n Pn minus 1 hat plus xn by n, that is for the nth value the estimate is given by the previous estimate multiplied by n minus 1 by n plus the nth observation divided by n. So that is the sequential formula for the mean value, or in other words the probability estimate here. So we use this formula. Now let us look at the MATLAB code. So first we have to determine or assume the number of trials. In this case, let us assume the number of trials n is equal to 1000 number of trials, and then we have to assume some true value for the probability. Here we assume that it is 0.4. So this is the value we want to find. That is the true value. Now we generate the random values. That is, we generate the Bernoulli random variable. So for this we will write a for loop where n is equal to, where I is equal to 1 to n. So for each loop, so in the each loop we generate this random variable x as a Bernoulli random variable with parameter P, that is given by P true, and then we use this value and practically in MATLAB what we will do is we use the binomial random generator, that is binorand, with n is equal to 1 and probability value P true. So we use this function in MATLAB. So for generating the Bernoulli random value or Bernoulli random variable. Now to get the estimate of the probability, what we do is we use this formula. Pi hat is given by Pi minus 1 hat multiplied by Ni minus 1 by I plus the current value, that is x, divided by I. So that gives us the latest estimate of the probability, and then we put it in a vector so that we can plot the estimates. So that is the end of the for loop. And next we just plot the probability estimate. Now let us look at the actual MATLAB code. So we can look at this MATLAB code here. N is equal to 1000, that is the number of trials. P true is the true value. P estimate, that is the initial estimate. We can assume it to be exactly at the center, that is 0.5. And then we begin the for loop. We have x is equal to this binorand of number of, that is n number of trials is n equal to 1, and then P true. So we get this random value x. And then from this we can update the estimate, that is Pst is equal to P underscore est into n minus 1 by n, that is nx minus 1 by nx, that is I minus 1 by I, and then we have the latest observation, that is x value divided by nx. This gives us the update of the estimate, and then we put it in a vector so that we can look at the evolution of the estimation, and then we plot the results. So here the blue line basically shows the estimate as we get the observations. So as the observations number increase, that is the number increases from say 1 to 1000, the estimate also becomes more and more stable and gets closer and closer to the true value. Here the red line shows the true value of the probability and the blue one shows the estimate. Now we can clearly see that there is a good convergence. There is a convergence as the number gets closer and closer to 1000. So to summarize, in this video we have looked at a simulation of the coin toss experiment in MATLAB. That is, we have a random value or random variable x that follows a Bernoulli distribution with probability parameter p, and then our goal is to find the value of the p from an observation. So we assume that xi are the outcomes from these observations. So it is the realizations of the random value x, random variable x. So xi and I is equal to 1 to n. So we have n observations. That is, we observe them sequentially, and then from maximum likelihood estimation of the Bernoulli parameter p, we have that p n hat is equal to average of the observations. And now for the sequential observations case, we have to rewrite this estimate as in a sequential form as given here, and then for the MATLAB code we write as follows. That is, the number of trials n is assumed to be 1000, p true for example 0.4, and then the for loop for I equal to 1 to n. So for each iteration we generate the random value using the binary rand function, and then we estimate the probability using a sequential estimation formula just discussed, and then we keep them for reference in a vector so that we can plot the results. Now let us look at the MATLAB code, and you can clearly see all the steps, and then we plot the results, p estimate vector, that is the actual estimate, and then we also plot the true value for reference. Note that when we do the iterations or this simulation again and again, the shape of the estimate, the curve, basically the estimates sequence will always change, because the values will always be different, because the values of the random variable x are always different in each simulation. So for every simulation you can expect the result to be different. For example, let us run it again. So we will get another curve, and similarly try again. You see we get another result. So the estimate is always different for different simulations, and however we can still observe a kind of convergence, and sometimes it will converge to the true value very closely, sometimes there will be some bias. So thus we have used MATLAB to simulate a Bernoulli random variable and estimate the parameter p of the Bernoulli random variable or the Bernoulli distribution using MATLAB code. Thanks for watching.